So hello everyone, welcome being here. So today we have Professor Zhang from Shanghai Jiao University, and let me briefly introduce him. Han received his bachelor and master degree, so both from the Department of Automation at Shanghai Jiao University in 2011 and 2014. So after that, he studied for his PhD degree from KTH Institute of Technology in Sweden and obtained degree in 2019. So he is current associate professor at the School of Automation and Intelligent Sensoring at Shanghai Jiao University. And Han will visit our GERAD for 3 months.
Yes.
Yeah. And his research lies at the intersection of control theory, optimization, statistical learning, and robotics, with a focus on inverse optimal control, strategic planning, and robotic perception, system identification, and their application to intelligence, robotics, and autonomous system. And today, I'm going to share his recent results on motion planning for robotic system. So let's welcome him.
Thanks a lot. Thanks for having me here. So it's always a privilege to present my work here. So my name is Han, and so today I will talk about some learning-enabled, but what I mean learning-enabled, this kind of thing is not this kind of end-to-end sort of thing. So that is currently not our focus. And also when I'll talk about some robot perception, so namely this feedback, where do you get the feedback information from? And then how do you solve this motion planning efficiently? So there are some videos that our research is about. So on the left-hand side, you see this rehabilitation robot, and then you have this human-robot coordination. So the question becomes like that. So everyone has a personalized sort of, the patient is different, and then their like need for rehabilitation is also different. And then as their sort of process goes on, the treatment process goes on, their need might also become different, because some you have muscle cramps and so everything becomes, so it evolves within the time. So then also on the other hand, you have leg wheel robots. So it is very efficient in traversing this kind of complex terrain. So, but and also on the other hand, when you talk about this this kind of navigation is through this. This is in Shanghai. It's a very crowded metro station. So how do you navigate through this kind of dynamic environment? And then you have people constantly moving. So how do you do that? So these three kind of things requires three different aspects. So of motion planning. So the first one, it becomes, so how do you satisfy this? What should be optimized? So namely, the optimization thing should be so the objective function should change to suit the personal need of the patients. And then the second one would become like, how do you get this robust post feedback from the environment? So namely, what we do is we do some little tricks on the SLAM technique. And third thing is that, okay, so how can you solve this problem efficiently? So namely, so all these three problems sort of falls into the scope of this optimal control problem. So the first one is that, okay, how can you decide the objective function of the entire problem? And the second one would be, okay, so probably you will have some chance constraints, because due to these errors in the prediction of your future pedestrian movement, there are some like uncertainties, and how can you deal with that? And also on the other hand, how can you get the post feedback? So namely, x1 equals to x bar, and x bar is get your post from your SLAM. So you do it iteratively like an NPC manner. But so my talk will focus on these three aspects. So the first one is inverse optimal control. So namely, which decide your objective function. And the second one, you decide how you can do the SLAM under extreme conditions. And then The third one is how do you solve these kind of problems? So the first one is inverse optimal control. So this is a little bit of motivation. So in nature, like agents tends to follow this optimality rules. For example, sensory motor, how can you reach for target? And then also how do you invest this investment portfolio? So you want to maximize everyone. If you talk to a manager like of funds, everyone has its own like criteria to optimize. And also in nature, like when to hatch a queen, because it's a balance between food and also like the population, and then you also have the vehicle takeover. So when do you cut the lane, and then when do you go back? So it's always like someone drives a little bit more aggressively, the other ones are defensive driving. So, but one of the fundamental of the optimal control or in reinforcement learning is which is the objective function that suits the best of the contextual environment. So on the sorry, I can use the. So this is the one of the robot that we designed. So by reinforcement learning, and then you can see that although it behaves quite well, like some in most of the places, and then it has to tune the reward function very carefully. This is the very consequence that you fail to do that, and then we have to fix the robot a lot. But anyway, so tuning is such a weighting parameter theta in the objective function. So it's composed of different features that you want to consider. It's highly relies on your experience and imagination. So the question is that, can we do that? Can we learn that from the experts? So you do a demonstration and then human show you how to do that. Can you sort of infer the objective function from the human's decision criteria? So the goal of inverse optimal control becomes learn the unknown objective function from the observed expert data. So also, AKA, this is also called inverse reinforcement learning. So depend on if you have the transition kernel or not. So, but the motivation becomes like, okay, so first, if I recover the objective function, I will know how do the experts make their decisions. You get an explicit model for their decision mechanisms. And the second one becomes, okay, so if you get a prediction model, so you get how this thing is organized, how this is making these decisions, then you can predict and imitate the expert behaviors. The third thing is that, okay, so since you have some explicit structures in your objective function, so compared to behavior cloning, you use more this kind of prior informations so that it is more robust to out of distribution samples, and also you probably need less data to train these kind of things. So, but here the key challenge is that, okay, so you observe the expert data, you can have a lot of noise, because due to the measurement errors and also the decision criteria might also be stochastic itself. Like I can either 50 chance going that way and 50 chance of going that way. So it very much depends on how the thing is like modeled. But the key challenge is that can we eliminate the estimation error by involving more data? So hopefully I can, by the end of the day, I can add more data to it, and then my theta estimation, or objective function, can converge to sort of the true sort of the objective function. And then this is what we call like consistency properties. So namely, it's robustness against noise. And the second one is that you have this local minima issues. So by the end of the day, if you result in a like a minimum, like a non-convex optimization problem, so everything is nonlinear. So you hopefully you can say that, okay, so your global optimal is statistically consistent, but what you actually like say that, okay, attain in practice is some local minima. So then this doesn't really make sense. I mean, so you can, of course, you can argue, but yeah, in practice it can never be achieved. So let's start with this linear quadratic IOC, inverse optimal control, as an entry point. Okay, so in this personalized rehabilitation training, so you have, especially with stroke patients, you have acute phase and recovery phase and chronic phase, this kind of three phases, roughly. So you have different patterns and needs, and every patient is also different. So we start with this kind of like cranking up this thing. So we set up a crank and a motor, and then this encoder will map this position to the screen. And I give a reference signal on the screen, and so that I will let the patients to sort of rotate the crank and then try to track the reference signal. It's a very typical like this kind of hand and eye coordination kind of things. But also the key aspect is that this the patients also need to try very hard. So if anything, so if I don't really care, so then it's not rehabilitation. So then the neurons won't sort of grow, sort of say, in his or her brain. So this, you need to sort of warn this mind drift during this training. So if you see a warning, so then the physician or the clinicians will say, okay, so it seems like you are not doing well, so what happened? So basically, this is the idea. So we want to model this, since everyone is different. So we want to model everyone's personalized preference in rehabilitation. Someone is maybe more aggressive. Someone is, okay, is a little bit lazy, but anyway, so we formulate it as follows, as this LQ problems. So this XR is basically the reference signal that we get. And we are trying to balance this thing between the tracking error and the control effort. Basically, it's a rough model. And then also one of the key problems that we have is that every time that you let the rehabilitation to start, so basically you will sort of, so 1, 2, 3, go, and then the patient will, there's a like random like time of like length that it starts tracking, but it doesn't really start at once. So that we do this formulation because we let it to sort of end at the same time, and then but the starting time is random. For example, the reference signal lasts for 10 seconds. Okay, so then the patient can start tracking based on his choice, like at 1 second, or like 1.5 seconds, or 58 seconds. But this is the idea. So we model that as sort of the before the agent starts tracking. So the control effort and X is 0, and then this kind of zero mean IID noise is added to this transition kernel. So namely, you have a shaken a little bit in your hands, and also sort of so the entire forward optimal control problem is formulated like that. So we first draw this realization, this initial point and X bar and N, this time tracking horizon time length N as a random variable from. So you draw that from a random variable, and then this objective, this optimal control problem is conditioned on the realization of these two factors, these two parameters. Okay. So with this in mind, so what we are trying to identify is the positive semi-definite matrix Q bar now. Okay. So the inverse optimal control tracking problem. So what you have is actually the axis, so the where it is at this angular position of X, and you have, suppose that you have M trials. I assume these are IID samples, okay? Because keep trying, and then what is a priori known is this system dynamics A and B, because you can always identify this motor, crank motor, and then A and B, and then you have the reference signal. And this process noise covariance sigma W, you can do this. You can identify that using experiment. But the goal is to identify Q. So how do we do that? So note that since you have process noise, so PMP, this punctual eigenmaximum principle, that doesn't work because that is open loop. So you basically write out the Bellman equation. That is your that is the optimality conditions. And on the right-hand side, you have the cost to go and this running cost. And on the left-hand side, you have this V. Note that you always have a minimum here. So namely, so on the right-hand side, is always larger than the left-hand side. So that's the Bellman inequality. This inequality has to hold for every x and u, every possible x and u. So therefore, you can define this kind of so-called Bellman residual. So the right minus the left. So that is always positive. And then the key idea is that we plug in the possibly noisy data x and u inside of the Bellman residual. And then we minimize the Bellman residual with respect to q under the constraint that this c, that is our Bellman residual, that is always non-negative. So how do we do that? So this is the stuff that we formulate. And then since this E, we approximate it with this IID samples by uniform law of large numbers. And then you can have this, right? And then, so we have a little bit problem with this, right? Because that's like infinite dimensional optimization. But you can, because due to we are thinking about this LQ case, so you can literally write it as like that. So this is always non-negative. It's equivalent to you have this matrix that is positive semi-definite. All right, so then you arrive at something that you can solve, which is an SDP. It's a convex optimization. So then, which arrives, so we can prove that the unique optimal coincide with the params to be estimated. So that is our Q bar. So, and also, how can we do, if we do this kind of, we plug in with IID samples, how can, will it converge to the true value as m goes to infinity? And yes, because the solution, we can use uniform law of large numbers and prove this and that, and then we arrive at the solution of the approximate optimization converges in probability to the true params, okay? So this is a little bit simulation, so you can see that the error goes down, and then the convergence rate is like most m estimators, is the O to the power of like m to the power of like minus half, something like around those lines. So it is a robust estimator because the local minima issue is solved. So we're solving this convex optimization, and then we can kill the noise effect by just adding samples. So, okay, so.
N here is the number, n trajectory?
Yes. So you let it try m times.
So that's 5,000 per
yes, but so that we are, so in practice, we don't really do that. So, but note that this is relative error. So because you have already, this is already 1%. So that is already like 100 or something like that. So if you want to really like go this far, of course, yes. But in practice, we don't really do that much. But anyway, so we apply this to rehabilitation. So of course, that's thanks for bringing that up. So this is also our concern as well. In practice, we didn't do exactly like that. So we do like apply, but that's another story. We do a little bit like Kalman filter and stuff like that, and then so we apply it to the rehabilitation. So we ask the patients to track the given reference signal with great concentration, for example, 10 times or 20 times. And we collect the data that which the patient is fully concentrated. Okay, so then we use this IOC to model the decision criteria that the patient is, so we can build a model that with full concentration, and then we ask the patients to recite the numbers, because we want to give some distraction to him. So for example, I ask 4, 7, 60, 65, and then he or she is required to say like in reverse order. So we increase the number of digits so that is a very sort of quantized methodology to measure the extent of the extraction. And then we define the score. So the error U, that is the error that between our predicted models, the predicted U and the true U. And then also the predicted X, sort of say, the angular velocity and then the angular position. And then we also do this kind of, because there are a lot of extreme points. So we just do this kind of, we use log 1p and means arise and median just encrypt to between -3 and 3. So then we arrive at a score. So in practice, you choose this alpha to be 0.5. which is the best. We have tried different alphas, but in this case, alpha is the half is the best. So we draw this ROC curve. So it's a like classification. So saying that if your patient is truly distracted or not. So then you can see that the red line is that based on our score, it is like that, and then the blue one is the if we use the reference signal itself to try as a model. So basically, you are supposing that the patients should sort of the tracking trajectory should lie close to the reference trajectory. So basically, you can use that as also a indicator of distraction. So you can see that the red line is always above the red line. So basically, what it says is that if you fix the false positive rate, so then you will see that the true positive rate is always larger than our baselines. And if you fix this true positive rate, then your false positive rate is also smaller than the baselines. So that shows it's a better indicator. On the other hand, so we also show that the score has a positive sort of kind of correspondence with respect to the number of digits. N is totally, there's no distractions. And then, so N is, for example, we let, for example, each patient to sort of recite until there's 85% of accuracy. Otherwise, then we minus 1 digit, minus 2 digits. And then you can see that as this one goes sort of, it has a positive kind of relationship, so to say. They are kind of linearly sort of correlated in a way. Okay, so now the problem becomes, that is LQ. So now what we are interested in is that, can we bring this thing further? So think about this nonlinear decision like Markov decision process, which means that you have a discount factor alpha, and Q is the transition kernel, and that this is the objective function. And then there's no closed form. The key challenge, if you still want to identify the theta, so which means there's no closed form of the value function here. So then what are you gonna do? So basically, the objective function is a structured gray box because it's a linear combination of the features, but the V is a black box. We don't know. So how can you do that? So then we use this occupancy measure. So we define the occupancy measure on this gamma x times this gamma a, like that. And then you can just try to write out the you can define the projection operator on this. So it's a marginalize out all of the U's. And this part is that you transition, that you move one step forward by this U. And then you define the time accumulated occupation measure that basically you add them all together. So then by this kind of construction, you can turn this thing into this infinite yet linear but yet infinite dimensional program. So namely, so you are optimizing over the mu, which is you're optimizing over all of the positive measures, positive sign measures. And then you have this, it's a kind of, that's a dual that's an integral. And then you have this P and Q are just linear operators that acts on this mu pi measure. And then you have this mu1, that is the initial distribution. So then you work out the Lagrangian of that with a proper kind of analysis. You can work out, okay, 3 optimality conditions. So namely, the first one is the dual infeasibility. And then you have the complementarity slackness. And then you have the primal infeasibility. Primal feasibility. Okay, let's look at this kind of primal feasibility conditions. So what is actually this? What are the adjoints? You can just try to write out what is the adjoints because you can just use this kind of thing because try to take your P and Q to the other side of of the commas, right? And then that becomes a joint. And then you can just write out joints of this Q star V and P star V, and you plug that inside. This happens to be your Bellman residual of your dual. Okay, so then what becomes, okay, so you are trying to minimize over this complementarity slackness while constrained by this kind of inequalities here. So it's basically the same story. Last that we talk about this LQ in IOC is just a special case of this one. All right, so then this becomes the infinite time accumulation mu pi, and then we only have the finite length of data because mu pi is just accumulation of infinite measures. And then you are optimizing over v and phi, per c, which is also the function space. You optimize over function spaces, and here this has to hold for every x and a. And this one, you have to add this kind of regularity conditions to eliminate the trivial solution. So basically, I mean, the objective function 0, it is optimal to every trajectories, right? So you have to show that there is at least some trajectories on the entire state and action space that is non-optimal. So this is basically to eliminate this. But what we are trying to do is that we're trying to solve these three problems in order to solve this kind of IOC, because you are dealing with a very complicated infinite dimensional program. So basically under this condition, so you will not visit basically what it says in the future. So under this condition, so you can actually show that you can replace this mu with this mu hat with finite time horizon mu, I would say. And then because they are kind of both absolutely continuous to each other. And then this is the first thing that we focus on solving this problem. And then this problem happens to, you can sort of, because this expectation, this integral, right, you can plug in with this IID samples inside. But there's a problem here. This has to hold for every x and a. So how can we do that? So then our problem becomes like, okay, so we first approximate with C and V by polynomials. So we use this Lagrangian interpolation. So basically, this is the interpolation nodes, and this is the interpolation basis. And R is, for example, the polynomial basis for V. And then by this kind of famous Putnam's positivity, this Stellan this kind of thing. So this V per C hat, which is a polynomial, is positive for every k, for every eta. So for every x and u. But if this is a sufficient condition if it belongs to this set. So namely u0 and u1 are a sum of square polynomials. Well, these g1s are just gi's are just constraints that constrains your entire action and state action space. So, and it is Archimedean, but I'll skip the details. But you can change your basis and arrive at this kind of equivalent formulation. So then the entire theorem, you have to say there's basically two consistencies. One is that, okay, so as m goes to infinity, the number of samples goes to infinity, what can I say? And as the order of polynomials goes to infinity, what can I say? So hopefully we can say the limit like this, right? So then let this be the optimal solution to the approximate problem. It holds that, so if these limits, you bring these limits to infinity, so this will be 0. So namely, the optimality conditions of the original problems is satisfied asymptotically. So this is the idea. So, but the order of the limits really matters. So as we said, so we want this limit of m is the first one, because why is that? In real practice, you always collect the number of data, right? You collect the data set, and then you try to crank up the polynomials order, and then to see if I can get a reasonable solution or not. Then if we say, okay, even if I tried a lot harder than that, I can still not able to get a very good solution. Then what else? Then I can collect more data. Right? So that's why we sort of really struggle to put the M in the first place here. So then this is okay. So now this is the first part of my talk, and then I will talk about more on this robust SLAM and this solving techniques. So now for this common robots sensors for the robots, they are basically categorized for example cameras and LiDAR sensors. And one thing that we would like to is that 40 millimeter wave radar. That is this project, by the way, is sponsored by ZF, this tier one suppliers for the commercial cars. So they have this radar sensors. As you can see, like camera and LiDAR measurements are sensitive to light conditions and the weather. For example, you have this kind of smoke and fog. And for example, on the raining, and then you can see that the rain drops, especially when you drive on the highway. There are this kind of rain stuff like is brought up by the forward cars, and then the LiDARs cannot penetrate. So, but this 40 millimeter wave radar is based on this magnetic radio magnetic wave measurement. So these doesn't affect it. But there's a price to pay. Is that the measurements are robust, but in extreme weather conditions, but extremely noisy and sparse point cloud. As you can see here, these like blue ones or purple ones are the LiDAR points, but these like snowflakes, kind of this noisy white ones are this point cloud brought by this 40 millimeter wave radar. So it is kind of noisy and sparse compared to, because you can barely see this kind of trees and here, but by this 40 millimeter wave radar. Okay, so then problem is that can we do SLAM using this one? So compared to this LiDAR, for the radar measurements, it gives this kind of information. So distance, like azimuth, and then you have this elevation here. So, and also there's one important factor for each point cloud, it also provides a radial Doppler velocity that is on this direction here. So you can use that extra information to do a lot of things. So the key challenge is that, okay, so the point cloud is noisy and sparse. So LiDAR measurements that are based on feature matching does not really work. We have tried, but it never worked. So this is our entire framework, like of the entire. So first of all, we have to do this data pre-processing in this step here. So there are a lot of ghost points, as you can see here. Let's see. And then you can see there's due to this multi-pass effect, because this radio magnetic wave will bounce multiple times on the ground. So it creates a lot of ghost points here under the ground. And you can see also there's a lot of these kind of unstable kind of dots somewhere here. So how can you do that? So we do a plane fitting here so that we remove the ghost points. And then we do some like this very, so if it shows up like in multiple frames, then we keep that. So we do a very simple kind of pre-processing to get to wash the data. And then for the ego velocity estimation, we can do this. So for a target point, suppose that it's this point has a velocity of VP. So if this point is static, so which means your sensor velocity will be exactly the opposite. So you can do this kind of, using this kind of thing, you can write out an equation. So basically your radial Doppler velocity is equals to m times the V radar. So, and you have a minus sign here. So with that in mind, but this equation does not hold if you see something that is moving. So you can use that as a constraint, and then you do a plane fitting with this ransack, so that you can easily remove this things that are dynamic. For example, you can see the car here. You do a plane fitting, and something is like outliers. So, but this is based on the assumption that most points that you see are static. So of course, like ego velocity estimation with linear regression based on these static points, you can easily get your velocity of your sensors. But then the problem is that, okay, so can we do this scan registration very well? So basically, it's a very sparse and noisy, and so how can you do that? So then we assume that each point in the point cloud is just an IID sample of the object's distribution in the environment. So because it emits one like radio magnetic wave, and then bounce back, and then you get one dot. So basically, this is the idea. So you assume that it's an IID sample, and then where the scan registration is to find the theta, the rotation translation between two frames of the point cloud. And note that the point cloud does not necessarily coincide even for the true theta zero, because it's noisy, right? You don't really. So, but the idea is that even though it is noisy and sparse, so the distribution of the point cloud is actually the same. So can you do that? How can you match these two distributions? So then the first thing that comes into our mind is to use the moment matching method. So then you have this generalized moments. We define phi. In this case, we use these Gaussian kernels, and then we construct these equations like moment matching equations, and we try to solve their moment matching problems. So it's statistically consistent estimator as long as the centers theta k are not on the same plane. That's we prove that. Okay. So then we do some experiments. This is simulation. This is the famous Stanford data set. We try to perturbate. This is a bunny. I don't know if you can see, and this is a dragon, right? This is armadillo. This is armadillo. But anyway, so we do a lot of noise perturbations inside, and then we keep adding this noise, but it does not affect at all by the noise because the noise is part of the distribution itself. Okay. And also on the other hand, so we try to crank up the noise deviations, as we can see, and also we increases the portion of outlier increases because we just scatter some salt in the point cloud, and then it also does not crank up. The error does not crank up compared to the others. Like for example, this well-known teaser plus plus. But like teaser plus plus really sort of because it's regarding the portion of overlap. When the portion of overlap decreases, still I mean the teaser plus plus still is the best one because it is optimized to have a minimum sort of overlap. But it is not better than ours in others simulation. So then we tested on the real vehicle. This is based on our own open data set. So this is our building. We just take a tool, and then you can see that ours you have this less kind of errors. And then this is sort of the this is the this is the sort of the entire kind of we run in our campus, which is 5 kilometers times 10 kilometers huge campus. And then you can see that that's roughly how it kind of looks like in the campus, sort of thing. Yeah, including this kind of loop closures and everything. Okay, so then we move on to some other problems. For example, this left wheel robot. So left wheel robot is efficient in moving and good at traversing barriers. For example, this kind of stairs. But this kind of sudden jolts will, when traversing these barriers, will make IMU pre-integration fail. So because this certain jolts may also affect this skewing process of this LiDAR frames. Because, for example, this that's how the time sequence of between the sensors. So you have one LiDAR measurement, but between them you have a lot of this IMU measurements because it's a much higher frequency sensors. And then for each LiDAR, LiDAR points, this is the like in R3, but for each LiDAR points, you have a timestamp. So you have to deskew that because it's a rotation kind of emission kind of a sensor. So you need to deskew that based on your sort of post estimation. And also, why this pre-integration might fail is that because this bias that you model in this IMU pre-integration is Brownian motion. So which is good for the slow kind of thing, but it's not apparently not true under the southern jaws. So this will affect this kind of Rij between these keyframes of this rotation, translation, estimation. And also this will affect this LiDAR deskewing kind of process. So that will let it sort of perform very poorly. So what we do, this is our sort of a preliminary work. We are still working on it. So this model terrain with radial basis function that we fit this RBF is because we scan the terrain, right? We fit it first with this radial basis function. We create a smooth surface. And then, but since this one decays exponentially fast with respect to R, so then you to sort of increase the efficiency, you have to choose your C, you place your center points around where this kind of, basically these LiDAR points are located. And also on the other hand, here you have, basically that's the same thing again, you plug in, you create the observation model, add some noises to your like observation, and then you create this PZ is equals to this, where this W is something that you want to fit. And then you take expectation on both hand side of this thing, and then conditional expectation, and then you construct the moment condition of that one. So this is your M. This part is your M of X. And then you try to sort of use a tower property, and then you can do this kind of thing, create this part is equals to the E of this M transpose times W. So you can fit the moment using this kind of things. So then, because this phi decays exponentially fast with R, so usually this M times M transpose is sparse and very ill-conditioned. So in order to, which means that you will have very kind of weird shapes on the RBF. So in order to mitigate this fact, we just choose to use the ridge regression. We add a regulation term lambda here. So then you can write this W hat K, your estimate on W, by using this kind of this thing. Because note that it's a summation over time and summation over the kernels. So which means that if you have the summation over time, you can do it online. So that you can do it with this online regression. So which means you can write it as a common filter type of thing. And due to fast decay properties, you don't have to update all WKs. So I just skipped the details, but on the other hand, so this, what we can do, once we get this manifold, how can we do that? So you remember that it has encoders on the two legs, which means that you know exactly where it was your foot will land, right? According to your joints position. So, but based on the forward kinematics. So you can do that. So you can construct a bunch of these kind of constraints. So namely on terrain and in wheel plane radius condition and normal collinearity. And then you just mix it up, try to add that in the objective of this scan matching. We use a loosely coupled like a framework so that because the tightly coupled, you have this IMU is too sort of strong in a sense. So we use this loosely coupled kind of framework. And then because we assume that you have a firm contact on the surface so that you can add that as an extra constraints in the LiDAR so that you can make everything work. So this is the demo video that we have. So so let's see. Oh. Oh, wait, let's see if I can control this. Oh. So I just fit the terrains using RBF, and then you can see the stairs and everything. And then there's a grass, it's kind of bumpy, so that you can see that it creates a fairly good estimation on the surface, and then you can take that as a constraint. And this is a smoke test, basically, because you can see our compared to other things, the stairs are really sharp. Like, for example, this kind of, but for the others, it's kind of smears. So this is a fast Leo 2, which is a well-known kind of thing. And then you have also the other things like left Kylo by like ETH, and then you can see that you have like the artifacts on the stairs. So some others doesn't even converge. For this one also have smears as well. So we also tested in some other like wild environment in the campus, for example, botanical garden, as we can see, but I don't know how to fast that. But this doesn't even like converge, so it's failed. So we do it on the in the rose garden. We by the way, this is we released the open data set. So this is you can see that there's an like double layer of artifact when it's traversing the stairs, climbing the stairs. You can see it's kind of consistent in a way. So I think Bowen knows a lot, like knows the place because when he gets he's studying in S3TU. But this is in the botanical garden, so there are like suspension bridges and everything, which is kind of challenging. And this leg kylo just will drift on the bridge, and then you can see here. But we managed to sort of give a consistent map. Yeah, I have more, but I will fast. So be fast. So the last thing, this is also sponsored by ZF, and then they want to have to deal with this tractor trailer motion planning. So because the challenge of the tractor trailer vehicle is under actuated, and you can have this jackknife effect that when it's traversing and make sharp turns, and then within the logistic part. So we do it, the application scenario is in a logistic park. So the on-road, we are trying to drive the topology node of the park sites while avoiding the obstacles. Well, in the parking scenarios, it's trying to dock to its sort of place of the warehouse. In this direction changes narrow spaces. So the framework will compose of two kind of parts. One is this on-road trajectory planning modules. So it is trying to use this geometry formulations to evaluate this kind of lateral and orientational errors, oriental errors, and also model that as in a cost function. And then you have this intuitive initial path generations, including this initial gas, find the homotopy class, and we solve this optimization problem. Once it gets the trajectory, so then we use that. The problem is that how can you track the trajectory well? So in that case, we use this Koopman bilinear model to track the entire thing. But so I don't have much time, but the basic thing is that we try to assume that the center lines is composed of basically two things. One is either a straight line, or when you turn, that's an arc, so to say. So then we write out the errors, geometry errors in this case. And then so for the how do we find this homotopy class on an intuitive initial pass is that we divide, because these kind of red kind of things are assumed to be obstacles. Our goal is to follow the center line, and then when the center pass is kind of the pass is wide, then you don't really divide we don't really sort of put that into the constraints. But when it's narrow, then you have to put in the constraints so that it gives like it solves this kind of gives you a little bit of more efficiency in this case. So that also when you plan a coarse pass, so the wide segment is the center line itself, and then we combine the coarse path segments, and then we just use the initial guess for the subsequent optimization. So the question is how can we solve that efficiently? We use this warm start techniques. So basically, so in the first place, we just set this kind of your boundary, this kind of kinematic constraint, because it was very complicated nonlinear equality constraints. We just put it in the objective function. And then the delta t between these samples, the delta t sample rate is relatively coarse. And then we try to solve that and get a very coarse kind of path. Very coarse kind of trajectories. And then we sort of try to cramp up the sample rate, sort of say. So you get a finer and finer sort of say, and use that like form a kind of optimization, the solution, optimal solution as the warm start that you start with. And then by the end of the day, you'll be arriving at a fairly good sort of trajectory. So then the problem becomes, how do you sort of track the planned trajectory? So in that case, we sort of construct this using this Koopman bilinear model here. So the idea is to use the Koopman bilinear model to fit this nonlinear kinematic model with unknown parameters, because in that case you can get a much like a more accurate linearization in this, because I don't want to put this thing inside my MPC. Otherwise, you're solving a very complex nonlinear problems in a very short time. That's not doable. So in that case, if you can do this, you can have almost something that is linear, so that you can write everything into a quadratic program. You can solve it with very fast in this way. So we construct like a derivative-based lifting function, and then by the end of the day, we can have this kind of thing here. So this is the bilinear term, but we just assume that, for example, zk is keeps the same when you actually like do this kind of for all in the time steps when you plan a thing. So that's a much but we do linearize things, but that's a much kind of accurate linearization compared to just to directly linearize throw away the terms like in the first place. So this is by the end of the day, we have this like scenario, and compared to state of art works, our approaches has the lowest mean cost and best optimization performance and higher success rate and the lowest mean max CPU time. So, and also this is the Koopman bilinear MPC, and then you can see that. So the idea is that the error that you have of the model is compared to direct linearization. That's very low, but you also is more efficient to solve this Koopman MPC. So this is a little bit of let's skip that because I have something that is this is the comparative experiment result. So you can see that is how the trajectory is planned. So here is supposed not to hit anything. So my student will try to move that thing, because then it's sort of plans really fast, sort of thing. But and then when you move this, it is still able to replan and track, stay on track. So, but then we also compare with the other like state-of-the-art solutions. So it is not as efficient. Then it's sort of colliding within the box. So you can see. So when it moves, it's such a short time, so it's just colliding into that. So then this is our ongoing work. So basically, we focus on this uncertainty-aware planning in narrow environments. So basically, the problem of existing, because you have localization errors, and then you have measurement errors, and then you have this uncertainties of the dynamic obstacles like moving in the environment. So how can you deal with this like uncertainties? So basically, we use this chance constraints. So the problem of existing uncertainty-aware planners is to approximate these vehicles as ellipsoid, but no feasible solutions in narrow environments. So that is not good. And also, it requires the distributions of the noises. They assume that to be Gaussian, which we don't like. So basically, if you see this thing has, this is for a rectangular thing. So it's just kind of, when it's sort of perturbates, it becomes like this kind of, like this shape, sort of thing. So we should take that into account. So the challenges also for uncertainty-aware planning in narrow environments is that the shape of the vehicle and obstacles, let's assume they are polygons, they have the collision avoidance is very complex. So the distribution of the noises are not Gaussian. So how can you do the collision probability? So the idea is that once we introduce this P, this chance constraints inside. So the biggest problem is that how can you define this distance between your vehicle and obstacle, which are polynomials? How can you do that? So which we have in this kind of existing work called the OBCA, which you can beautifully transform this thing into a dual kind of optimization like formulation. But still, how can you deal with this P? We don't have the distribution of P, and then we can't solve this this problem within this probability constraints. So this is not possible. So the overall formulations. So the overall formulation becomes like, so the challenge in solving such a optimization control problem, as I said, there's no explicit formulation deal with the dual constraints. So we formulate the distance between the polygons. So the idea is that we use this OBCA, and then the distance can be written into this kind of things. So you replace this distance with this kind of within a bracket with this kind of things. So, but still, that is within the probability. How can you do that? So, and the distance has an explicit solution, but how can you, I will skip the details, but our work is trying to sort of how to tighten the constraints a bit. So you lose some kind of feasibility, but you get something stronger that you can deal with. So we try to get out this lambdas and mu's out of this P so that you can, by the end of the day, you can deal with something that is. And then this piece here, we have something like Wasserstein distance and try to bound it with this reference signal, but reference distribution. But anyway, so next we transform the chance constraints into deterministic constraints. And then the idea is that we use this Wasserstein distribution, distributionally robust. We create a Wasserstein ambiguity set. And then we manage to change everything into the deterministic constraints so that everything here, E, you can calculate this expectation and this sigma you can calculate. So you can push it to the off-the-shelf solver. So that is the parallel project. So can I just play this thing? Okay, so you can see this thing is shaking a bit. So with this OBCA, so you can see that our thing is trying to sort of defensively driving. So you can just directly park inside, but that is a little bit too dangerous. So sort of we decide to let this guy pass and then try to in parallel parking. So compared to the original one, so we have a better success rate and collision and fewer collision numbers. So and also, so this is OBCA, right? So on the corridor that we also trying to do a lot of simulation tests, and as you can assume that. So there's something wrong with the, but anyway, so we can see that our algorithms just is kind of behaves really well. The other ones you can either have this collision or you can have this like freezing robot problem. So it is not going. So it guarantees the safety and avoids over conservatism. And then we do some experiment tests. So with the real robot, so our intelligent wheelchair, and then you can see this. There are some like estimation errors on the future trajectories, and we are parking it to a very extremely narrow kind of parking spot. And see, it is quite narrow here, so that it's sort of trying to sort of wiggle around inside. So because he doesn't really know what the bicycle is trying to do, right? So trying to wiggle inside, and then, but the other ones, because they just failed because they use ellipsoid, and then it's too conservative, and then you can see here there's actually, due to the localization and perception errors, it is kind of like shaky. So, but and then we are trying to so in parking, so we are trying to park in a very extremely narrow kind of environment. So this space we have only like 10 centimeters wide according to this, and then it is successfully managed to park in the parking spot, and then while the others just fail. So we do have some comments by the reviewers, and then they say you shouldn't do like something that only you succeed and others all fail. So we are working on that as well. So okay, so finally, I would like to thank my sponsors, the Nature Science Foundation Council of China, and also the Municipal Science Foundation of Shanghai, and also ZF, and also my collaborators in the lab and my collaborators in Chalmers and Uppsala. And thanks for your attention.
Thanks for the very interesting talk. And is there any question for our speaker? Is there any question from the online audience? So I do have a question regarding the nonlinear inverse optimal control.
Oh, yeah, sure.
So you claim that when you have sufficient data, so the performance can be, almost sure converts to the.
Oh, not the nonlinear ones, because it also like requires this so-called identifiability, because then it's the structure of the problem itself. So in general, these inverse problems are ill-posed because you are trying to optimize in an infinite dimension. Because, for example, like zero function is always optimal to everything, right? So it all depends on how you pose the problems. So if you have a very clever choice of phi or something, you can put the structures to it, then probably you will converge to the true things. But for the nonlinear case, what you can really to sort of say is that you can converge to the true optimality conditions. So namely, you can have some model that describes the data.
So I'm also curious about the scalability. So for this type of nonlinear problem, so almost all the methods we need to select some dysfunction, and so usually a high dimensional dysfunction can provide good performance, but if these two.
Yeah, that's the you are really asking the $1 million question here. So recall that we have so this thing has to hold for all x and a. So that's a very difficult problem to tackle. So the best we can do is we use this Lassalle's framework. We use the sum of square polynomials. But there's a huge but here. So your dimensions will sort of blow up exponentially fast, because as you can see, even you have two interpolation nodes for one x dimension, then that is 2 to the power of n. That blows up very fast. So we really have to find a way other than polynomials to make this inequality happen. So this is the really $1 million question. So we are working on it, but so far we are also trying to use the V, for example, this neural networks to express that. But so far we are not making any progress right now. So because you can't really just find out a nice way to make it non-negative. That's the problem. So yeah. Yes.
So you have considered the distribution robust optimization, and you mentioned that the ellipsoid set is not performing well.
Sorry?
Ellipsoid set.
Yes.
Not performing well compared to Wasserstein. So how do you compare with scale divergence set?
So the thing becomes like this. So we are still using this Gaussian, but the thing becomes like you create an ambiguity set outside of this Gaussian thing. You allow it to approximate it with this, the reference distribution is still Gaussian, but you get some space of wiggle, so that then you take that kind of approximation error into account when you solve the problem. So you give a more sort of non-over conservatism in the problem. So, but the reference distribution is still a Gaussian, like ellipsoid. I will get back to that sort of thing. So here, so this thing is still kind of if you want to get this kind of thing, you have to assume that your reference distribution is ellipsoid. But then you use the Wasserstein distance sort of to play around and to wiggle around in this distributionally robust kind of ambiguity set, and then you get something like that. Then this kind of thing you try to minimize within this value at risk kind of thing, and then you get this.
My second question is why I have considered Robotic by minimizing this value at risk for the C bar into objective function.
Yes, but by the end of the day, you have minimizing the value at risk. But then what's the distribution of that? So then you have to find out the P, the distribution P that lies within the Marshall-Stein ambiguity set. That's the idea. So then you sort of can remove the sort of the P. You get a deterministic kind of like optimization. So that's the idea. But I have never considered like directly minimizing over the value at risk, but depends on the problem, like what is the probability distribution that you consider, right? So value at risk, you try to optimize over for example, over a set. The worst case, the P that you have, the probability density that you have within the set that you define the value at risk, right? So then the problems is like how can you deal with this problem? So that's the I don't know if that answers your questions.
So if you go back to your slide, just trying to remember and summarize. So it was a pure radar slide.
Yeah, it's you mean this one?
No, the radar part.
The radar one. Yeah, it's a pure radar slam. It's not LiDAR. But it's because this you don't need pre-integration. You do need pre-integration, but you don't use IMU because you can it has Doppler velocity. You can have an estimation on the velocity itself by the.
But you're combining, so you're not combining with any other. So you still have a LiDAR and a camera.
No, that's
so you're not combining.
Not yet, but we are working on combining with cameras because that's a perfect fit between these tools because radars are extremely robust, but it has sparse point cloud and noisy. But these cameras, you can have a very rich features and not sparse at all, right? But it's sort of non-robust. But for this project, so the ZF explicitly requires not to use other sensors, only by the
I'm
radar.
just wondering why they're interested in this mapping part. I mean, I can understand that the localization part is of interest, but the mapping from very sparse point cloud, like if you show the last.
You mean this one?
You get, I mean, I don't know. Yeah, the previous
yes.
one, yeah. Is it like what do they do with this type of map?
Oh, so it is not that sparse because that's sort of a you layer multiple frames up, so it still gets something. So it's not compared to LiDARs, but it still gives you a point cloud sort of thing. So it's not that sparse if you stack multiple like frames together, the key frames together. So for each frame we get like for example like 20, but you stack for example 6 like local keyframes together, which is already dense.
Any other questions?